Hi, I'm Jacqueline and I work for Imperial College London. I'm the project leader for the multi-scale modelling project and now also a co-investigator looking at whole systems models, incorporating techno-economics and life cycle analysis. In today's talk, I'm going to give you an overview of what sustainability means in terms of batteries, why it's a complex problem, and why it needs holistic solutions. I won't go into the details of this slide because I'm sure many of you already know something about lithium-ion batteries. But this is just to show you the complexity of how many different chemistries there are. They're all made of different materials and they have different properties. And all of this affects their sustainability. The life cycle of a lithium-ion battery covers a number of different stages, from raw materials extraction through processing of those materials, manufacturing the components of the cell, such as the electrodes, and assembling them into cells, modules, and packs, then integrating this into electric vehicles and using them for however long. At the moment, these batteries are fated to end up in landfill, and along the way, certain impacts are incurred, such as habitat destruction, resource depletion, energy consumption and its associated emissions, the use of fresh water, and the use and release of toxic chemicals. One small step we can take towards improving the situation would be to recycle batteries. We can start by defining what it means for batteries to be sustainable. The general definition of sustainability is around safeguarding the resources of today so that future generations have access to them as well. There are a number of impact factors which are incurred, which fall within the three pillars of sustainability of society, economy, and environment. In general, a sustainable battery would follow the principles of green chemistry and green engineering, have a circular economy, and also consider the principles of reduce, reuse, recycle. In order to choose the most appropriate battery for any particular application, we need robust tools that can track all of these factors along the entire life cycle. The relative sustainability of any battery depends on a large number of factors. The materials that go into the battery incur different impacts depending on where they come from, how they are extracted, and how they are processed. The manufacturing process can have high impacts, particularly if they use electricity sources heavily dependent on fossil fuels. Since the use phase is the longest stage of the life cycle, the performance and lifetime of the battery greatly influences its overall impact. But end-of-life processing is important too, particularly if the batteries end up in landfill. If they are instead recycled, the processes involved may incur impacts too, and if it is difficult to separate the component materials, then recycling becomes more expensive and less appealing. The number of distribution steps between each stage of the life cycle can be considerable too, especially if long distances are involved. Complex problems often involve trade-offs, as illustrated here in the example of lithium iron phosphate. From a purely materials point of view, they seem fairly ideal. Iron is relatively abundant, although phosphate is considered critical by many nations. The materials are fairly safe to process. They don't require very high temperatures. They're chemically stable, and we can use aqueous processing. However, LFP has low energy density, which means that you need to use more material to achieve the same range, and that means more weight. LFP is thermally stable and tends to have quite long cycle lives. But the low value of the materials mean that they're less attractive to recycle. However, we still don't want them to end up in landfills because degraded LFP batteries can still catch fire. So this shows you that it's not just about materials. We need to consider other factors such as cell design, pack design, how you operate the pack, etc. And so we need to take a holistic approach to balance all the trade-offs across the life cycle. Looking at the bigger picture, the scale of the problem is such that we need to act fast to implement low-impact recycling. There are many predictions showing an exponential rise in sales of electric vehicles. Last year, there were 10 million electric vehicles on the roads globally. So this means around 10 million should reach their end of life by about 2030. So we need to be ready to collect and recycle them, particularly as degraded batteries cannot be safely stockpiled or landfilled. So the question really should be not can we afford to recycle, but can we afford not to recycle? Most of the impacts are incurred during extraction of raw materials. This slide is a visual montage showing you the vast array of different impacts that need to be taken into account. There's destruction of habitat, particularly for important ecosystems. There's depletion of fresh water, which impacts local communities and ecosystems, particularly in arid regions. Mining processes emit a wide range of pollutants, either into the air or into the water. Mining waste dumps are in themselves physically hazardous, but they also contain very high concentrations of heavy metals. The materials that are mined themselves, particularly nickel and cobalt, are in fact toxic to work with. The energy consumed during mining processes tend to be quite high, and those have associated greenhouse gas emissions. And then there's also the question of whether natural resources will last. The issue of habitat destruction is close to my heart, as I've always been a strong supporter of nature conservation. This map shows the most important terrestrial ecoregions as defined by the World Wildlife Fund as regions of high biodiversity and fragility. Now we overlay these with the regions having lithium deposits, followed by those high in nickel and cobalt, and then graphite, all key materials for lithium-ion batteries. As you can see, there's quite an annoying overlap between the regions we need to protect and materials needed for batteries. It looks a bit like the planet's developed measles, and now we add a rash of gigafactory sites. This montage summarizes the impacts incurred during the manufacturing step. There's habitat destruction from the aforementioned gigafactories. There's depletion of fresh water. There's direct emissions, particularly sulfur dioxide. There's a range of nasty chemicals involved. And then there's also high energy consumption, which particularly if it's in a region which uses a lot of fossil fuels in its electricity mix, there's high emissions from this stage. Battery. You may think that battery electric vehicles don't really incur many impacts during their use phase, and this is largely true. However, the electricity mix is important. In some countries, electricity generation still has very high associated emissions. EVs still emit particulate matter as their tires and brakes wear down. This is not new and is a problem for internal combustion vehicles as well, but it's still an issue that needs to be resolved. If you spotted a pattern, you'll have noticed that habitat destruction is back. This is particularly a case if we have to build new infrastructure to accommodate electric cars alongside internal combustion vehicles as we transition. The impacts at end of life depend on whether we recycle or landfill batteries. In both cases, there is the potential for habitat destruction, particularly on where the landfill or recycling plants are sited. Recycling processes use energy and emit pollutants and also use a range of hazardous chemicals, but these impacts could be worse if degraded batteries catch fire in a landfill site. There are impacts which can only be seen when we look across the entire life cycle. Here we consider spatial logistics. At the moment, raw materials are largely transported to China for processing. From here, battery materials or whole cells would be shipped to Europe and North America. And if recycling centers remain clustered within China, they'll have to be shipped back for recycling at their eventual end of life. So the first step would be to distribute recycling centers across the globe so we can avoid these steps. These long-haul transport pathways have quite severe implications for cost, safety, and incur additional emissions. So the key message for supply chains is they should be localized as much as possible, and this will also then retain strategic value of the materials. The temporal logistics reveal just how complex the recycling problem really is, as EV batteries tend to have quite long lives, somewhere between 8 and 15 years. By that time, the technologies will have moved on. We'll be using new cell chemistries, new manufacturing methods. So it's quite tricky to work out how to weave those materials back into the manufacturing stream. Add to that the problem of whether those materials still perform as well as they should. It also shows that recycling can't solve the problems of raw material extraction, or at least not for a long time, because it's quite a long time before those materials start to displace virgin materials. So we still need to find solutions to the early stage impacts. So I've introduced all the problems. Now it's time to consider what solutions we have. If we consider each life cycle stage, there are a number of things we can do. For example, in the extraction stage, Materials are an important part of the equation, so certainly we can choose more abundant materials, but also try to use as much recycled content as possible. We need to avoid placing new mines, particularly in fragile or pristine areas. The use of green energy and green chemistry principles throughout. Mines should be encouraged to try and extract all the metals rather than just one or two. Mining waste dumps and perhaps tailings should also be reprocessed to see if we can extract something from them. But there are also mining processes which are less damaging, such as lithium extraction from geothermal brines. Looking at the manufacture stage, it's really important that we design cells and packs so that they're easier to take apart. We need to improve our resource and energy efficiency throughout. We need to make sure that the cells and the electrodes that we make are of high quality, and this has a lot to do with the microstructure that we achieve. Again, use of green energy and green chemistry principles. Trying to use aqueous-based processing if we can, and designing cells also to be as modular as possible, which means you could swap out defective cells and not have to replace the entire pack. At the use phase, if it's possible to extend the lifetime in certain applications, this is good. There are certain engineering solutions you can apply, such as thermal management to control the operating temperature, which then controls many of the degradation mechanisms. Battery management systems can also deploy algorithms which can minimize damage to batteries. It might be possible to recondition battery cells and packs. You can obviously extend the life of any product by putting it out for a second life. In some cases, this makes logistical sense. It's important to make sure that for any application, we're matching the technology so that it is the best fit for that application. And the charging electricity used should obviously be decarbonized as much as possible. The recycling processes, it's important to make sure that we are collecting as much as possible and to increase the efficiencies of recycling processes, also using much more low impact processing. So there are three main recycling methods. There's pyrometallurgical, hydrometallurgical, and direct recycling. And it's generally found that direct recycling is more effective and actually has a higher yield of high value materials. Again, use of green energy and green chemistry principles, and also trying to upcycle materials wherever possible. There are holistic improvements that we can apply across the life cycle. It's important to ensure that the lessons that we learn through recycling batteries are fed back to the earlier phases. So the materials that we choose, the cells and the pack designs are more amenable to recycling. Batteries should be clearly labeled. One of the things that makes recycling so difficult is the fact that there are so many different chemistries. And so clear labels would allow us to separate them quite easily. The supply chain should be localized as much as possible to reduce the distribution distances and the impacts associated with those. If batteries could have passports showing how they've been used, it would be easier to work out their state of health. And this would be useful for both recycling safety, but also second life use. And it's important not to forget the distribution steps and any packaging involved in that. They should be accounted for in any kind of life cycle assessment. And finally, I will introduce you to some of the work that we've been doing to improve holistic assessment of batteries. Earlier this year, we published some work on the lifetime extension strategy of thermal management to see if adding these pack level mitigations are worth the extra cost. We compared a range of thermal management strategies to see which ones give the most benefit. Our model extended BATPAC, developed by Argonne National Lab, to include thermal management through the strategies of air cooling, immersion cooling, and tab cooling. This work was done in conjunction with other researchers in our group who have developed optimized tab cooling, and this has led to a new metric called the cell cooling coefficient to encourage better pack design for thermal management. We found that while simple tab cooling by itself did not improve life cycle cost and carbon footprint, the optimized tab cooling, by more effectively controlling the operating temperature of the cells, greatly extended their usable life, and this in turn improved both life cycle cost and carbon footprint. Also this year, we published work on pack disassembly to explore the financial viability of recycling commercially available EV packs and to see which pack designs are easier to dismantle and thus more profitable. We also compared costs of dismantling packs in different countries, which affects the labor costs and also the costs of distribution. In addition, we compared the three recycling techniques, pyrometallurgy, hydrometallurgy, and direct recycling, to see which ones are the most effective. Pyrometallurgical recycling is the most widely used, but it's also the most expensive because of the very high temperatures you need to smelt the minerals. Our results show that packs that had fewer modules and which avoid welding and glues cost much less to take apart. For low-value materials such as LFP, pyrometallurgical recycling is just too expensive, especially because you can't get the value back from the materials. And so in these cases, you might need to use direct recycling. And we were also quite surprised at how expensive shipping is as well. So this all suggests that we should try and localize supply chains, use direct recycling wherever possible, and design our packs so that they're easy to take apart. And so that's it. That's the end of the talk. I hope that gave you a nice overview of sustainability and why it's such a complex problem. I'd like to thank you for your attention and encourage anyone who'd like to get in touch to discuss the work to do so. Thank you. Bye.